Hi, in this video, we want to take a look at statistical models of time series. All right, so this is just an introductory look, and we just want to get a feel for what we're doing from a statistics point of view when we're working with time series. All right, so our objective is for us to build a mathematical model that gives a good description of the data that we're working with. All right, so let's say that we have a time series of observed data. So x of 1 is the first observation, x of 2 is the second observation, x of 3 is the third, and so on. So what we're going to have is that each individual point of time is going to be a distinct observation, and we want to somehow come up with a mathematical model for this. Now, we're going to call our the collection of random variables. We're going to denote that in this manner in set notation, and it's going to be indexed by t. Typically t is for time, and we're going to refer to this as a stochastic process. Most of the time, t is going to be discrete, and usually t will be of like 1, 2, 3, 4, 5, and so on. It's possible also to have negative time from before a benchmark or a reference level from going backwards. It's possible to have other fractional times that would make sense if, let's say, that we want to have our index in terms of years. Then I could have individual months or weeks or days as fractions of a year. Would also be possible for t. Typically, it's integers. Most of the time, you're going to see me put things down as whole number values. And the observed data is called the realization of our stochastic process. Now, the very most important way for us to handle our data, to work with it, to understand what's going on, is going to be visualization. We're going to be thinking with our eyes. And so when we do that, what we're going to do, we're going to plot the horizontal axis will correspond to time. The vertical axis will correspond to the actual values we observe from our data. So we'll put along the horizontal axis t, vertical axis will be the actual observed number. Frequently, we're going to connect the dots that we get and to get a hypothetical continuous time series. Now, when we're plotting, usually if I have distinct discrete values, what we're going to do, we'll put down dots. If it's going to be something that is a continuous random variable, something that is changing something like height or temperature, that we don't have true like jumps, like explosive jumps or complete changes instantaneously, we will have lines. Typically in time series, we have plot lines. Now, something that is important to be mindful of when we look at our data is that the appearance that we see from when we look at our numbers, it can change completely depending on our sampling rate. So let's say something is happening every second, but I sample every minute. Well, there's going to be a lot of changes going on in there that I'm going to miss because I'm completely, I'm completely insufficient on my sampling rate. So a good example of this actually happening in real life is when you look at a video of wheels or a helicopter. You look at a car going down the road, and it looks like the wheels are going backwards instead of forwards because the camera is not picking up enough frames for it to look like the actual real life situation. Or you can look at a helicopter turning in a video. Let's say you see you see the blade starting, you know which way it's going. Well, after a bit in the video, it looks like it's going backwards because of the sampling rate wasn't fast enough to capture all of to capture the true direction of rotation. Now, this distortion, this phenomenon is called aliasing. Now, the fundamental visual characteristic distinguishing different series is their differing degrees of smoothness. One possible explanation for this smoothness is that it is being induced by correlation between adjacent points. So the points of the series at time t depend on past values. So a big part of our time series analysis will be looking at, hey, do we have correlation between consecutive values? Think about temperature. What temperature is it now compared to the temperature it was 2 minutes ago? Well, it's going to be relatively close. It might be getting warmer, it might be getting colder, but the actual number is going to be close to each other compared to, like, let's say 6 months ago. So one thing that will be important to us is the correlation of our observations over time. So, like, if I'm talking about the temperature, well, the temperature now is going to be more strongly correlated with the temperature 2 seconds ago than the temperature, 3 days ago. All right, so something that we're going to be using a lot is white noise, and there's going to be 3 flavors of this. Most of the time, we're going to go with the Gaussian white noise for most aspects, because mathematically it is the most complete, and it works out nicely. But really, we can make things a little bit more general and go with the other 2 also. So we've got 2 types. This is regular white noise. We have IID white noise, and then we have Gaussian white noise. All right, so Gaussian white noise has the most properties. It has the most narrow description, while general white noise is looser in what the definition is. So here we have uncorrelated, that doesn't mean independent, but uncorrelated observations with each other. We have mean zero, and we have constant variance with respect to time. The variance doesn't change over time. IID white noise, here we're going to say that they're independent, identically distributed. Notice that we didn't have independence and we didn't have identically distributed with regular white noise. Once again, we have mean zero, constant variance with respect to time. Now, Gaussian white noise is IID white noise, but we're going to say that we have the normal distribution, the bell curve, the Gaussian distribution. Once again, mean zero, constant variance with respect to time. All right, so a simple kind of generate time series that we can do is to just take a collection of uncorrelated random variables with mean zero and a finite variance. And so time series generated from uncorrelated variables is used as a model for noise. And so so what we're going to do is, when I have time series data, I know that there's going to be, like, fluctuations going on around, like, the true, like, signal. And to model the fluctuations that we're really not interested in, that cause problems for us, we're just going to call it white noise, and we're going to model it frequently as Gaussian white noise. And we're going to denote it as W sub t. And we could also say it is, white noise distributed. Now, where does this term white noise come from? Like, if you read DC Comics, Cyborg has a white noise generator cannon on his arm. It's got the same. All right. The white designation comes from white light with all possible periodic oscillations are present with equal strength. So that's where the original term white noise comes from. We will sometimes refer to the noise as independent, identically distributed random variables. And when I do that, I will go IID, mean zero, constant variance with respect to time. In general, if it's not specified, assume that it's Gaussian white noise. And, Gaussian white noise is independent, identically distributed, normally distributed, mean zero, constant variance. All right, so let's just look at an example. So here's some R code. I'm just generating some uncorrelated, independent, identically distributed normal random variables. And so this just gives me an example of a Gaussian white noise time series. So here, this is like, there's no relationship between this. There's no reason to analyze this as a time series process at all. This is going to be the noise that makes it harder for us to see the signal in our time series. All right, so let's look at a different type of modeling situation. Let's say that we're doing moving averages and filtering. So let's say that we want to replace the white noise series by a moving average that smooths it out. So just as an example, we're going to replace that white noise that we have by its average of the current value and its two nearest neighbors. So I've got one value from the past, one value in the future, and the current value. And I'm just going to take the average of them. And this is going to smooth out that time series. And we'll notice that it's going to be smoother than the original. And we'll notice slower oscillations. And we'll notice that the faster oscillations are taken out, and a lot of the extreme values are going to be removed. So to do this, we're going to take the filter function. We want in both directions, past and future. And then here, I'm just using 1/3 as the weights of each of the terms. And this will give us that moving average. And so here is the original data. Here, we just looked at this a moment ago. I look here at the next plot. You notice that it's a lot smoother and it's a lot less extreme on this. So you'll notice if I come up here, how this is fluctuating, below -3, almost to 3 up here. Here we have the same scale, but you notice it's not reaching those high peaks because it's been smoothed out. The oscillations are not as sharp, they're not as extreme. Now, another statistical model that we'll be talking about in future videos is autoregressions. So autoregression is basically linear regression on past observations. And so this is going to be a major tool in our tool belt. So here, we're going to be we'll be using autoregression when we see oscillatory sinusoidal behavior. And so in those cases, moving averages are not going to be the appropriate model. So we're going to want to use a different type of model for this quasi-periodic behavior. So if I see oscillatory sinusoidal behavior, that should immediately tip me off to I probably want to use autoregression. So here is just an example. What we're going to do, we're going to go with a degree 2 autoregression process. So I take the previous observation, I subtract 0.9 times the observation before that, and then I'm going to add on a white noise term to account for the fluctuations that I see. And this is going to be our autoregressive process. So now here, this is like the random variable itself. This is not the actual trained model built on data. This is my theoretical model. So the equation represents a regression on of the current value on the previous two values. That's why we call it autoregression. Now, a problem with this structure is that on the first two values, I don't have anything to set up. So like if I want to run this model on, for x sub 1, x sub 0, I don't have any past ones to build it off of. And we're going to end up getting periodic behavior in the time series. And so if I just go ahead and say that x sub 1 is a white noise term, x sub 2, I'm going to say is just 2 consecutive white noises just to kick things off. So how do I get this set up? So here I'm going to go ahead and just to give you an example of generating it, this is not real data, this is generated data. I'm going to take some white noise and then I'm going to apply auto regression onto it. And then we'll go ahead and plot it. And you'll notice a very strong oscillatory behavior off of this. Now, another possibility that we could observe for a mathematical model would be a random walk. Now, random walk, we take our current states, and then we have a random change in our position. Okay, so that's a random walk. Now, a random walk with drift is when I take my position, I take an overall trend, and then I add on a random value. And so here, a random walk with drift, my current value is equal to my current value plus the overall trend plus some randomness. This randomness is where the random walk part comes in. And so typically we're going to say our very first value is at 0 to kick us off. And we're going to call that trend the drift. If the drift is equal to 0, we're going to call it just a regular old random walk. And if you take a stochastic processes course, you will study this up, down, left, and right, get to know this very well. Now, if I take this equation and I start working out the details, very easily I can see that my current value is equal to that drift times the number of steps plus the sum of the random variable. All right, so let's go ahead and generate an example of this. So I'm going to set the seed so that I can reproduce the results. Here is going to be that random term in the random walk. Now I'm going to invoke this part of the formula. For this part of the formula, I'm just going to take the sum, the cumulative sum of all of the random values. And then I'm going to tack on my drift. Now in the plotting, I'm plotting some lines on here. Here's 2 straight lines for us. And so now we can see that random walk. So here's the random walk with the drift. Here's the random walk without the drift. And so the black line is the drift without the randomness. Here, the blue is when I don't have the drift, what would the drift term be because it's equal to 0. Now the next example, we're going to use some trigonometry. And so there's a lot of different ways to go about this. Typically, we're going to be using a sine or cosine. We'll try to use the sum to angle formulas to compress down to fewer trigonometry items if we can. All right, so we want a model for our time series, assuming that our signal is coming from a constant periodic process contaminated by some random fluctuations. All right, so just as an example, we're going to go 2 times cosine of 2 pi times t plus 15 over 50 plus a random term. All right, so A here is going to be the amplitude. So if I have sine or cosine, A times the trig function A will be the maximum and the minimum values we observe from the trig portion. Omega is going to be the frequency of the oscillation. So we'll have one cycle per 1 over omega. And then phi is going to be our phase shift. And so here, you notice I have 2 pi. So remember that sine and cosine are 2 pi periodic. And so here, we write this in this very particular manner to make it easier to identify and communicate certain features. To make the trig functions naturally like 2 pi, but real life data, typically doesn't really want to adhere to 2 pi as its period. So to make it easier to convert from trigonometry to actual real world, we'll go ahead and put this 2 pi in there. The degree of which the signal is obscured depends on the amplitude of the or the amount of variation in the random noise term. The ratio of the amplitude to the signal, the amplitude of the signal to the noise is sometimes called the signal to noise ratio. The larger the signal to noise ratio, the easier it is for us to detect the signal that we want. Typically, we do not observe the signal, but the signal obscured by noise. So to mathematically write that out, we'll say that there's a signal plus the noise is what we actually observe in our data. We want the signal, we don't want the noise. And we typically will model the noise as white noise or some autoregressive term. When that noise term is autoregressive, we're going to call it a state space model. And so just for an example, let's go ahead and build something out using cosine. So let's go ahead and use cosine of 2 pi times t divided by 50 plus 0.6 times pi as my phase shift. All right, and here is going to be my noise term. I'm just going to be using random normal. So here is my signal. Here is my noise. And then here is the signal portion. If I put it down, here's the signal plus noise. So here we can visually see the trend, but it's not exactly going the way we want it to. It's not smooth. The smooth part is what we actually want. Now here, if I crank up the noise aspect, now it just looks like gobbledygook. I don't see that pattern anymore. So just to look at that again, so let's say that the noise is practically 0. Then this is what we're going to see. We get a little bit of noise. I mean, not a whole lot. We can still see the signal, but once that noise gets too big, now it's just gobbledygook. There's nothing to pull out. All right, well, that's all I've got for you. Life is short. Do math.